There's a field of mathematics called number theory, and although number theory is an incredibly large field of which I have a limited experience with it, there's a very interesting perspective that number theorists take in regards to numbers. Now, these are mathematicians who are channeling an ancient kind of attention to numbers, the most fundamental building blocks of numbers that we're aware of, which are the natural numbers. And when you look at these numbers and you try to understand these numbers, a really interesting fact emerges. And that fact is that there's really only two types of whole numbers ever. There are either the prime numbers or there are composite numbers, but that's it. So if you think for a moment that you can understand, if you take time to understand the prime numbers, the truth is that you are understanding all of the numbers. And so for a quick example, you don't need to understand the number 10 as a separate idea. You could instead understand the number 2 and understand the number 5. That if you only understand those two different building blocks, you can build your way back up to 10. And even more so than that, you can build yourself to any common multiple between 2 and 5. And you can even expand on that and say there are only specific numbers that could possibly be built up to from 2 and 5. And those would be the numbers that end in 0, not in 5. So if you understand 2 and you understand 5, you've created a basis by which to understand every number that is either 10 or a multiple of 10. And so this is why most computers, especially those that are responsible for encryption or hiding your data, rely heavily on prime numbers. Because if they can get a general understanding of prime numbers and store all of those in their memory, everything else just simply becomes a consequence. Now, we've talked about polynomials, where polynomials are these numbers that we have created, and we have created them through some of the simplest operations that we're aware of in algebra: addition, subtraction, and multiplication. And what I'd like to show you is that whether you're talking about polynomials, which are really just numbers that we have created and that we don't necessarily know everything we would like to know about them, or whether or not you're talking about whole numbers where the answer is just a whole number, these actually share a very common idea, which is that if you can factor them or if you can break them down to their primes, then you're going to see all of the details you need without having to go through the headache of trying to understand the result. So let's go back to our notes where we had just finished talking about doing equations based on pictures. And so from here, I'd like to just do a quick little reminder that if we have something that is of the form like x times x plus 6 minus 5 times x plus 6, really what this means is that I have x groups of x plus 6, some number that I grew by 6, and then I have 5 more groups of x plus 6 that I've made into the opposite. So let me show you how we can look at that. If I wanted to say I have x groups of x plus 6, perhaps I say that x, I'll just call x this kind of straight rectangle here, and I'll call this x because I'm going to say that it's x units long by 1 unit high. So that means the inside size of it is x. So for example, if x was 5, this would be a 5 by 1 rectangle, which is just 5 units large. So this is an x rectangle, something that I'm not quite sure exactly how big or how small it is, but we'll put it like that. So I have x groups of x plus 6. So let's go ahead and remove some of this so it doesn't get confusing. We'll just say I have x groups, now that we understand where it all comes from. I have x groups of x plus 6. So I'm going to say here's x, and here is my plus 6. And if x is going to simply be this rectangle, I'm going to say 6 is going to be 6 units long. 1, 2, 3, 4, I'm running out of space, 5, and we'll put 6 up here. And so if you squish all this together, you would get a 6 by 1 rectangle, but we'll keep them as separate units for now. So x groups of x plus 6 would get us so many of these x blocks that would go all the way down. And so I would have x groups of x. And in fact, most of the time we've been drawing this as a square, because if I have the same number of things, then that's just going to create a square, in fact, an x square. So we can clean that up a little bit. And we'll say that if I have x groups of x, that just gets me an x square. And if I have x groups of 6, then that means that I have 6 x's. And that's just because we can look at multiplication as either being forward or backwards. 6 groups of 5 would be the same as 5 groups of 6, so x groups of 6 would be the same as 6 groups of x. And so we're going to get 6 of these little x blocks that result from having that commonality. All right, what about this 5 groups of x plus 6? Okay, so now instead of x groups of 5 and 6, we're going to create 5 groups of x and 6. And I'm going to put a little block here so we start to divvy out our mind into these columns that I'm about to organize. And so if I have 5 groups of x, that's going to be 1 group of x, 2 groups of x, 3 groups of x, 4 groups of x, and 5 groups of x. Okay, so I've got my 5 groups of x, and then I have my 5 groups of 6. So it's going to be 1 group of 1, 2, 3, 4, 5. 1 group of 5, 2 groups of 5, 3 groups of 5, 4 groups of 5, 5 groups of 5, and 6 groups of 5. Good. So I've got 5 groups of 6 or 6 groups of 5, either way, and I have to remember that I'm going to make all of these opposite. These are negative numbers, so I'll shade those in. And I'll say that if you shade all of that in, all the way through, that what we've created is a rectangle, and we created this rectangle from some references, right? So we'll finish shading all these in. And we can show all of this with a picture and say that really what I've done is I started with x plus 5 by x plus 6, and that got me a total of an x squared, 6 x's, the opposite of 5 x's, and the opposite of 30. Well, since you have these kind of commonalities, we could write it in the dimensions of the shape, x plus 5 and x plus 6. Or sorry, x minus 5, because I had to do the opposite of it. So instead of it being 5 units long, it was the opposite of 5 units long. Let me correct that. Opposite of 5 units long, we'll erase and make that into a subtraction sign. So I can talk about all of these pieces that I've created either as a common pile that I have over here, or I could break it into an organized rectangle that says I have x minus 5 and x plus 6. And so another way of thinking about this is that everything that we have on the inside really just represents a number. The moment you tell me what x is, I can put it in and I will get exactly what the dimensions are to a number. But what I've been able to find out is that that number can actually be factored, meaning it's a composite number. It's not a prime number. It's a number that came to be from 2 other numbers. So it's interesting to think that we might be able to find the fundamental building blocks of just about any expression we've ever wanted, regardless of whether or not it comes out as a number or whether or not it comes out as something that has variables. Okay, the other interesting part of this is to see what it actually means to factor. If you look at x plus 6 here, this x plus 6 could be thought of as saying that it's a common entity here, and it's a common entity here, and so we pulled it out front. And that's a really improper math word, because really what we want to look at here is that we really undid the distribution we would have had to do if we started on this right column, where we take the whole x minus 5 and we distribute it to the x, and then we distribute it to the plus 6. So that would have got me x groups of x minus 5 and x groups of x plus 6. Or an opposite of 5 groups of x plus 6. So this idea of distributing we're familiar with. Now we're learning factoring, this idea of pulling out, or really geometrically finding a common side. Okay, so lots to kind of talk through there. Here we did another example where we talked about how these opposite blocks could really be thought of as to cancel away with some others. So sometimes we can even simplify our expression even more. And if we start with this x squared and an x, let's look for those common sides. Let's see if we can recognize what's happening. First, what do we have over here? Well, we had x groups of x and 2. So we had x groups of x and 2. And then here, we might have wanted to reorganize these so that the opposites were aligned. And if I had done so, I would have had the opposite of one group of x and 2, and I would have had a regular group of x and 2. So you could think of that as the opposite of x and 2. And you put a negative 1 out there if you really want. And then one group of x and 2, which again, you could put a little 1 out front if you really wanted to. But again, what's the common side? You could think of this a couple different ways. You could think of this as being a common side where you have a common side of x and plus 1 and negative 1. So that would be x plus 1 minus 1. Or you could think of it as a common side of x plus 2. X plus 2, because after all, that's the sides, the dimensions of this shape that we created. Here we had x plus 2, right? X is this big, and then we had plus 1 and plus 1. Over here we had x, and then we had all of this got me a full length of -1, and all this got me a full length of +1. Of course, if you simplify this up a little bit, you're going to see that you can look at this through a different perspective, which is that all this can simply be written as x times x plus 2. In other words, this row up here is really the only thing I need to capture the full meaning, and that's because the last two rows are really going to cancel away. If I wanted to draw a general picture for the rectangle that we've been creating when we've been factoring, it would be something like this. We have in the top right where we put our x squares, but if we have more than one x square, we would need to still be able to organize that in terms of a rectangle. So we would get some amount of x squares going sideways, some amount of x squares going up and down. We'd have x squares filling up the entire top left, because if I could get them all organized as a rectangle, then I'm well on my way to organizing the entire thing as a rectangle. That's no problem. In the bottom right, we would be putting our little C unit blocks, so I could put our little C unit blocks here, and all of this would need to be organized as some kind of rectangle. And then that would fill up the entire bottom right. And then in the top right and the bottom left, this would need to be our B's. This is our B X blocks, right? Where we've been organizing some of them, these ones going sideways, and so we would organize all of these up. We'd fill this all in. We would have the same number of rows because we're still having those common sides. And then I would do the same thing all the way down. And then I would just change my perspective a little bit for the top right. Over here, I would have those rectangles that are organized vertically so that they line up again with my X blocks, my X sides and my X sides all line up. And this would be our common picture for our strategies so far for organizing this rectangle. And just to kind of add a little bit to our notes here, so in the top left, what we're looking at is that we have, these are our A X squares is the amount that we have there. So we can put that, I'll make it a little thinner, our A X squares are all that top left. Our bottom is our C, just C unit blocks. So I'll make sure that's just C down there. And then we put some amount of B's in the top right. Maybe I'll call that B1. Of these X's, I put some of my X blocks in the top right. And then I made sure the value was the same, resulting with combining it with some of the ones in the bottom left. So sometimes I made the bottom left be positive as well to add up. Maybe I made them negative so that they cancel some of them away. But that's been the overall strategy so far, is put our X squared blocks in the top right, put our unit blocks in the bottom, and then split up our B so that we get this nice organized rectangle. Now that becomes more challenging when we take a look at problems like we have here to the left, because we now have to not only organize C, but then also organize A, and that's even before we're able to organize B. We've got so many different things, it's like a really hard Sudoku puzzle. So let's take a look real quick, like for this diagram here. I'm gonna do this 7x squared, and I'm gonna try to solve this just using intuition. You're gonna see how challenging it is. So we know that in the top, it's gonna be 7 of these x squares are all going to be organized in the top left, and so obviously that's going to have to be either be a 7 by 1 or a 1 by 7. So we're going to have 1x squared here and 7x squares, or 7 x's that are here, so that when they add up together or multiply together, they get our 7x squares. So I've got a 1x by 7x rectangle that gets me something 7x squared big. Okay, that part's okay. What about this 6? I suppose I could organize that as either -1 times +6, -2 times +3, -3 times +2, or -6 times +1. And I've got to choose if that goes up here or down here for each of those. That gives me, let's see, 1, 2, 3, 4 different options for the top right. And then 4 different options. I've got to check 8 different things. That's so challenging. Okay. And then on top of that, I need to check all of that against the fact that the top right here and the bottom left here have to add up to this -x. Because -x alone is going to go, I mean, that's only one of these little rectangles. So I'm probably going to need to create more and then balance that out somewhere else. this becomes challenging. So let's start off instead with looking at how this problem was solved, and then I'll bring you into the derivation in just a moment of how we could probably come up with a procedure to do this more strategically moving forward. Let's first just see whether or not this solution works. So we have 7x squared minus 6, or minus x minus 6, and it looks like the person who's solving this decided to take that negative x and transform it into a negative 7x and a plus 6x. How did they do that? How did they know to split that up in such a way? Not entirely obvious quite yet, but let's assume that that's our little star. However they did that is not quite known right now. It's magical, but we'll believe that they did. And so they did that. What did they do next? Well, we can understand the next procedure. The next procedure is that they looked at factoring out 7x from the first two terms, because if I have 7x times x, that got me back to my 7x squared, and my 7x times negative 1 got me back to a negative 7x. So in our picture, I guess what we could represent as happening is we had our 7x squared, and then we had our negative 7x here, so that we had the common side of 7x. That seems good. And then the creating that negative 7x was really putting a 6x over here. We had to create 6 more of them to balance it out, keep that meaning. That works out fine. So like a Sudoku puzzle, what times 1x gets me 6x? That must have put the 6 up here. And then, let's see, what else did we have? What times 7x gets me negative 7x? That must have been a negative 1 that goes here. And then 6 and negative 1 gets me my negative 6. That works out just fine. That was where I started. So it looks like this is a solution. And it looks like most of the process that worked out here is that they found this way to split up the middle term in just the right way, that they could factor out the first two to find a common side, a common factor. They could factor out the last two to find a common side, a common factor. And then after they created the 7x and the 6, which are right here, everything else just kind of flowed. The x minus 1 revealed itself. That was right here. And they got the full dimensions of the rectangle, a 7x plus 6 by an x minus 1 rectangle. Now that's really interesting. That's not an obvious solution. How was it that the person who solved that was able to find that? Was it through a lot of trial and error? Or is there perhaps a strategic way that we could look at solving this in the future? And that's the interesting question. But it's important for the next part of our notes to recognize that all of this work hinges on two different ideas. The first idea is that we have to find out this kind of star step that happens here. How was it that whoever solved this knew to break up negative x into a negative 7x and a positive 6x? Yes, it has the same meaning, but they could have broken it up any number of ways. They could have broken it up into a negative 4x and a positive 3. How did they know to break it up into a negative 7x and a positive 6? Was it just because of the first number and the last number that they tried to match it? Maybe. Okay, we could look into that one. And then let's see, what did they do after that step? So we'll explore the star step in just a moment. Oh, and then after that they did what's called factor by grouping. That was where they essentially grouped, they associated these first two terms, and then they factored out something common to them. So they factored that first group, and then they associated these last two terms, and they factored something out of that group. And then they factored once again. They found the x minus 1 was common, and so they read this off as 7x groups of x minus 1, and 6 groups of x minus 1 could be rethought of as 7x and 6 groups of x minus 1. Okay, not too difficult. A little bit hidden, but not too difficult. So in the next part, what I'm going to show you is how I believe the derivation of this first star step really occurred. How was it that somebody knew to split it up in just this exact same way? Okay, so we have the goals. We're going to try to find an instruction, a recipe for finding out if I am given any kind of quadratic. And so we'll write that using variables ax squared plus bx plus c. I'm given any kind of quadratic, and I want to know how to take this rectangle and identify it as a rectangle. So I'm believing that this is a rectangle. How can I actually write it all out? So let's see. We know that we're going to organize it in the same common way that's been working for us so far. So let's see how we would organize that. We would be organizing that so we put the ax squared at the top right, no problem. The c value has been going in the bottom right. That's been working out really well. And then we've been we kind of work in this like a Sudoku puzzle, right? Where we say we have the ax squared, we have the c, and then depending on what I can multiply a to, I'm going to try to find some numbers that go here and here, and then I'm going to try to find some numbers that go here and here that work out in such a way that this number and this number combine to get me my bx. Okay, so we've fleshed this out a little bit. How can I write this a little differently? Well, I'd like to get bx in my picture, so let's go ahead and put that in there. Do I put it at the top right? No, because bx is kind of going to be split. There's going to be some in the top right and some in the bottom left that both affect to bx. Okay, so we'll put part of b in the top right. I'll call that b1. b1x, that'll be part of b goes in the top, and then part of b goes into the bottom, no problem. All right, so I've got all of this, and then I'm going to be breaking this into a rectangle with dimensions. What are those dimensions going to be? Well, I know I'm going to have some amount of x's that are organized here, and I'm going to have something with x that goes over here. I don't know how many, so again, we're going to have to use even more variables. So I've got a, b, c, maybe I'll use d. d x's are going to go in the top right, and then I've got e x's that'll go on the top left, or in the very top, and then I'll have e x's that go to the left. That seems okay. And then I need, let's see, I'm going to get some kind of add or subtract numbers, so I'll just say adding f. There'll be some sort of amount of f's number unit blocks that go over here. I don't know how much f is. F could even be negative, so we'll just say I have f over there, and then I would have g, so I get this symmetry at the very end. Okay, so that means that all in all, I could write this now a couple of different ways, and this is an important note. This is how mathematicians really try to go through creating processes and rules and all the algorithms that we've been taught to memorize, like the Pythagorean theorem. It's just from playing. It's from playing and writing out everything on the paper, and then taking a step back and waiting for insight and coming back to the problem and really just building up that resilience. So that's what we're going to try to model here. I'm going to walk us all through that. We now have said that there's nothing that in every single one of these problems so far, we are always splitting this ax squared stays the same, but the bx always seems to split up. We always seem to split it up into b1x and b2x, some kind of splitting up that allows us to then form into our rectangle. I'm good with that, so I'll say plus c, and that eventually allows us to write all of this as a rectangle, where the rectangle has even newer numbers, dx plus f being the size of one side, and on the other side you have ex plus g, and that gets you the size of the other side. Okay, that seems like it's capturing everything that we've been doing. I can even go one step more, and I could even write kind of a bridge between all of this, and I could say that if you had started instead with the dimensions of the side, if you had started right here with all of this, and you had distributed instead of trying to factor, that would have just been that foiling or that double distribution we've been practicing. You'd multiply your dx times ex, and you would get dex squared. You would multiply dx times g, and you would get plus dgx. You would multiply f times ex, and you'd get efx. And then you would multiply f times g, and you'd get plus fg. Okay, so what we've now found is that we've captured every single way that we've played with this rectangle so far on the paper. Not bad. I'm not quite sure what it got us, but it definitely is true. We can even highlight the commonalities, right? We've got our ax squared becomes this ax squared becomes, oh, I guess this dex squared, and it's hidden somewhere in this parenthesis. I've even got, let's see if we can do some more colors. This b1x and this b2x came from bx, and is actually going to be this dgx and this efx. And then we have c. C is this, let's see, this number here, and that gets us this c, and it gets us this fg, and all of that is hidden in this parenthesis. How could we come up with a process for saying I'm starting here and I would like to end up here? And so this is a difficult problem. And so I'm going to walk you through the way that I imagine that somebody might have tried to solve this. They probably started off by saying, well, I recognize that the two numbers I don't affect at all are probably this ax squared and c. These stay pretty consistent all the way through. I've got ax squared appears here and c appears here. Even here, this is really just d and e is a, x squared, and then fg is really just c, so it stays the same all the way through. Then we can even write that out. We'll say that a here is equal to d times e, and c is equal to f times g. And then what else do we have? Well, I guess we have our b1 and our b2, so we've got b, which is equal to b1 plus b2, is really just dg plus ef. And so, okay, what are we staring at here? We got four letters that seem to keep popping up back and forth if we want to eventually get to our answer. We need 4 answers. We need D, F, E, and G. How do they play? How do they interact? And it's after staring at this and staring at this and staring at this that we might recognize that hidden in this A value and hidden in this C value are all 4 letters. In fact, if I was even able to just say something like A and I maybe multiplied it by C, that would be D times E times F times G. Or another way of thinking about it would be D times G times E times F. Oh, isn't that interesting? We found a connection between this A number and this C number that seem not to change, and this B number which seems to change a whole lot. One is the multiplication of 2 things, the other is the addition of those other 2 things. So I actually only need to find 2 pieces of information to do all of this, and this might seem a little bit obvious now that we're looking at it in hindsight, but really what all I need to do is I just need to find B1 and B2, because if I can find B1 and B2, and these numbers add to my B, of course, and they multiply to A times C, which is right here, right? D times G equals E times F. This is really just B1 times B2. And so really B1 and B2 are the crux of it all. If I can find 2 numbers that multiply to A times C and that add to B, I should have all of the information I need for this entire problem. Now, if that lost you, let's take a moment. I'm going to show you an example. And after I do, I want you to go back into our derivation. I want you to see why this works, because we just talked about it all above, but I'm going to give you a numbers example to help kind of make this clear. Let's say that I was given something like the last one I had, 7x squared minus x minus 6. And I wanted to know how to break this into a rectangle. Well, I just need to find 2 numbers, B1 and B2, such that B1 plus B2 add to -1, and B1 times B2 multiply to A times C, which is 7 times -6, so -42. And we could organize our thoughts a little bit like this. Let's do it like this. Maybe you've seen this before. We'll put -42 at the top, and we'll put -1 at the bottom, and I'm looking for 2 numbers, B1 and B2, that multiply to -42 and then add to -1. So let's think about what that might be. We'll put that over here. -42 in a table, and we'll say what multiplies to -42? -1 and 42, for sure. Let's do -2 and 21. That works. -3 and what would that be? 16? No. Ooh, what would that be? 14? 14. 3 and 14. Okay. -4 and that doesn't work. -5, no. -6. I'm not thinking -6 were. Oh, -6. Yeah, -6 and 7 works out. Oh, I think we're close. In fact, I want to do -7 and 6, and I think there we have it. There are our 2 numbers. These are 2 numbers that multiply to -42 and that add to -1. So let's do B1 equals -7. Let's do B2 equals 6, and then work through our problem. I can start by splitting up my -x into those 2 numbers, -7x and then plus 6x. And then I'll do -6, carry that down. And then from here, I should be able to find a common side. I should have found everything that I need to now be able to do my grouping and then my regrouping. In fact, on the left-hand side, I can pull out my 7x. That gets me x minus 1. And on the right hand, let's see, terms, I have pulling out 6 gives me x minus 1. And then here we have it, 7x plus 6 equals x minus 1. 4 lines of work with a little bit of scratch work over here, not too bad. So how did we do this again? Well, again, we were always trying to find a way to split up all of these terms and organize them in such a way that we could write it as a rectangle with common sides. We could do that factoring. And up here, we went through all of that exploration of saying the way that we could strategically break this up is by recognizing that all the information I need is hidden in A and hidden in C. It's just that if I recognize that the two numbers, A and C, multiply to my hidden missing links, then I can then use my missing links to break up the middle. That might seem like a little bit of magic, but really this is about taking time, looking at a problem, looking at it through different perspectives, recognizing a pattern, and then pulling it out. This is what true mathematics looks like. It's looking at things that's extending our intuition beyond common sense so that we can find patterns we didn't know originally existed. Let me show you again how powerful this is, because we'll use it with a new problem. I'll make one up off the top of my head real quick. So let's do 6x squared. Let's do 5x plus 1. Okay, so this is the pile that I have a rectangle in my mind for. Can we figure out how big it is? Well, step 1. If we take A and multiply it by C, that should give us the common pieces that I need for my rectangle. So here we go. A times C is 6 times 1. It's the first coefficient times the last coefficient. So that gets me 6. And so then step 2 would be find numbers B1 and B2 such that they multiply to 6 and add to 5. Okay, so what would that be? Things that multiply to 6 would be 1 and 6. They'd be 2 and 3. Oh, there we have it, 2 and 3. So B1 and B2 are going to be 2 and 3. So B1 equals 2 and B2 equals 3. From there, step 3 is just factor by grouping. So this would be 6x squared plus 3x plus 2x plus 1, which would give me 3x times, 2x plus 1, and then plus 2x plus 1. That works out well. And so if I pull out the 2x plus 1 from the first term and I factor it out of the second term as well, that leaves me a 3x and 1 groups of 2x plus 1. Wild. We've created a very simple method by which we can solve quadratics. We can factor them even if the beginning number isn't as nice and clean as we've been working with. Even though if the leading coefficient isn't equal to 1, it's no difficult. This is what's referred to as the AC method. And it's important to understand the AC method seems magical and it seems like a procedure that we follow because it works, but it's more about the discovery about it. How did we find this procedure? From somebody playing around with changing perspectives in the exact same way we've been doing until they found a magical missing link. That idea that A times C has the exact same components as B. So how can we factor problems like this? Well, we've got enough information now from all of our playing that we should be able to recognize that if we have 4 terms and if there's any kind of commonalities, that a really good important step is to start with this factor by grouping. So let's start with our factoring by grouping. I look here and I see that there is a x squared that could be taken out of both of these, factored out of both of these. So I could factor out x squared from my x cubed, that gets me x, and I could factor out an x squared from my 9x squared, and that gets me just a 9 left over. Then I'm going to put a plus sign. This is a common mistake that I see a lot of people make. We lose this plus sign here. But keep in mind, all we had in the beginning was a pile of things. Now I've organized some of those things into a common side in my picture, but there's still just addition happening between the two shapes that I'm making so that I get a pile at the end of all of this. Okay, so we have x squared times x plus 9 plus, what can I pull out of or factor out of 4x and 36? probably not an x because the 36 doesn't have one, but I could probably pull out a 4. So I'll factor out a 4. That's going to leave behind x and then plus 9. And so at the very end of this, I can recognize again this commonality, this ability to factor, where I have my x plus 9 common with my x plus 9, and I could read that to myself as saying that I have x squared and 4 groups of x plus 9, because I had x squared groups of x plus 9 and 4 groups of x plus 9. So here we are, fully factored that original expression. Now, I claim that if you subtract two squares from each other, regardless of what they are, you can always transform what remains into a rectangle. Now that's a bold claim. How could I do that? I'm thinking in my head that after playing around with all this, I've come up with a hypothesis. My hypothesis is that if I was to take any of these two squares that I could build up and I took them subtracted from each other, that the result would always be able to form a rectangle. Do you think this is true? How could we possibly do this? Would we have to go through all the numbers? Well, no, we want to think about the exact same way that we had just solved the last procedure we were looking to solve, which was let's try to express things with variables. Let's try to express things with pictures. Let's try to change our perspective so that we can get to a piece of truth. And so this is the claim that I am making. The claim I make is that if you subtract two squares from each other, and so I'll write that out. I have an x square and I have maybe an a square. So I'm going to say I have an x squared and an a square. And if I subtract those two, I claim that you can always make this into a rectangle. Is that true? Yeah, it is true. And here's why. I could write this as x plus a times x minus a. Don't believe me? Let's check. Let's try doing that distribution. X plus a distributed to the x and then distributed to the negative a would get me x groups of x plus a, and the opposite of a groups of x plus a. And then I could distribute all of this out too. X times x plus a would get me x squared plus ax. And then my opposite of a groups of x would be the opposite of a groups of x, and the opposite of a groups of a would be the opposite of a squares. And then those middle terms cancel out, and it looks like I'm left with exactly where I started in the beginning, which is that I have x squared minus a squared. X squared minus a squared. So that's kind of wild. That tells me that if you make a square out of any two whole numbers, and then you take away one square's worth of those components from the other, you will always be able to write what results in a rectangle. That's a pattern that doesn't seem immediately obvious. Picture-wise, what that means is that if I draw a square and I cut out another square from that I will always be able to write that as a rectangle where one of the sides I have is x plus a long, and the other side will always be x minus a long. So let's see what that means. That means that if I had a number like 100 and I took away 36 from it, that I would always be able to write the result of that in terms of a multiplication, in terms of a rectangle. And specifically this one here would be, one would be, 16 units long, and the other one would be 4 units long. I have a 16 by 4 rectangle, and that happens from subtracting these two squares. Don't believe me? Let's check it out. I have 10 squared minus 6 squared. That's another way of writing 100 and minus 36, right? Is 10 squared minus 6 squared? Well, using what we have over here to the right, I could write that as 10 minus 6 times 10 plus 6, or vice versa. I'll make this one plus 6 and the other one minus 6. 10 minus 6. And so I want you to take a moment and put that into your calculator. Does that actually work? Let's see, 100 minus 36 would be 64. And 16 times 4 would be, I think, 64. Yeah, it's true. It has to be true. And it has to be true for any two numbers that you choose, because we were able to prove it using variables. So we don't need numbers. We're able to prove this for anything that you were to come up with. Wildly, wildly powerful what happens when you allow yourself to just play in the realm of pictures and variables. So here you have it. This is what's called the equation. This is a very famous equation. This is called the equation for the difference of two squares. Difference meaning subtraction. So here we are. The difference of two squares can always be written in this way that we have. So let's take a look. Is there a way to factor a difference of two cubes. Can I factor it like this? A cubed minus b cubed, is that a thing? Turns out it is, and I'll tell you what the answer is before I tell you how to prove that. So we have that the difference of two cubes, if I take two cubes and I subtract them from each other, so I'll do maybe a smaller cube here. If I take a cube away from a cube, that will always get me something that could be written as a rectangle. That's pretty wild, and I'll show you what it is. A cubed minus b cubed is equal to a minus b times a squared plus ab plus b squared. Those are going to be the dimensions of my rectangle. Don't believe me? Let's check it out again. We're going to do the same distribution. We've got a minus b, and we're going to be distributing it to all of these different terms, okay? So a minus b times a squared would be a squared times a minus b. And then ab times all of that would be ab times a minus b. And then b squared times all of that would be b squared times a minus b. And so a squared times a minus b gets me a cubed minus a squared b. And then I got ab times a gets me a squared b. And then I have ab times negative b gets me negative ab squared. And then I have the last two terms would be b squared times a gets me ab squared. And then b squared times negative b gets me negative b cubed, I think. Okay, is there some simplification we can do here? I think so. Negative a squared b and a positive a squared b are going to cancel away. That works well. Negative ab squared and a positive ab squared cancels away. That works well. And so I think all in all, at the end of this, we're left back with a cubed minus b cubed. And here we have it. Again, our original formula must have been true because I could get at it from one way or the other. So here we have the difference of two cubes. That's a formula. That means that I could reorganize shapes, and depending on how I initially formed those shapes, I could always organize them back into a rectangle. In other words, if I ever subtract two cubes from each other, as long as those cubes were made from whole numbers, that's going to result in a number that is also not prime. It's also a composite. It's also something that can be broken down further and organized as a rectangle. Okay, is there a way to do a cubed plus a plus b cubed? Again, yes. It turns out that if you add two cubes together, if you add the amount of things in one cube and you add the amount of things in another cube together, you're always going to get enough stuff that you can reorganize that in a rectangle. And I'll show you what the equation is for it so that you can use it in your homework. But as far as proving it, I want you to practice the same distribution we did above. So the equation is that a cubed plus b cubed is equal to a plus b times a squared minus ab plus b squared. And I claim that if you go through the process of distributing this entire right-hand side the same way that we just did above, you're going to find out that this rectangle, this a plus b dimension by a squared minus ab plus b squared dimension rectangle, this rectangle will give you all of the material you need to be able to form a cube out of A and form a cube out of B and add it together and have the same amount of stuff on both sides. Now, how I'm remembering all this comes from a mnemonic. I'm remembering this from a memory tool. I'll tell you the memory tool so you can use this in your homework, and it makes memorizing it a little bit easier. But what I'm about to say isn't a proof. The proof is what you're going to do, just similar to what we did over here. You're going to show that if you start from everything on the right-hand side, it gets you everything on the left-hand side. But I will give you a tool that helps to kind of remind you of this in the future. And so the acronym, or the mnemonic that goes along with this, is SOAP. And so SOAP is a mnemonic, it's a little acronym that will help you to remember these two equations, the ones for the difference of two cubes and the one for the sum of two cubes. And it goes like this. S stands for same, so we get same. O stands for opposite. A stands for always. And P stands for positive. And I'll show you how we use this. So if I was to be given something like, let's say I was given 8 plus 64, and I wanted to be able to factor this and see whether or not this factors. The way you can always do it is you can say that the first thing is always going to be that you're going to make this look like the difference of, or the sum of 2 cubes. So I've got 2 cubed plus what times what times what gets me 64? I think that'd be 4, right? 4 cubed. All right. So here's how you could organize it. The first thing is you're going to do that first term, that 2, right? So the symbol between them is going to be the same as the symbol we have between the 2 cubes. So that's our same portion. So same means plus in this case because it started from plus. So plus means plus, keeping it the same. Same. And then I'm going to put down the component for the second cube. So I've got my a cubed and b cubed are turning into just a's and b's like the equation above. So I have the same symbol as the positive. Opposite would be the next symbol. So that's going to be, let's see, my a squared would be 2 squared. The opposite of addition would be subtraction. So same opposite. And then I do a times b, that would be 2 times 4. So same opposite, and then always positive. The last symbol is always a plus sign. So always positive, and then I put in my b squared there, which would be 4 squared. So all in all, I know that if I take 8 and I add it to 64, that will be able to be written as 2 plus 4 is 6, times 2 squared would be 4, minus 8 would be negative 4, plus 16 I think would be 12, so that'd be 12. 6 times 12 should get me the same thing as 8 plus 6, should get me the same thing as the addition of those cubes, and every single way you look at it, it's the exact same thing.